Cilia. As just said, my name is Leif Bredeson. This summer I worked on hydropower and pump storage hydropower on the Railbelt. Um, yeah, so this project was part of the Railbelt decarbonization pathways study. And that study had a lot of goals, including significantly reducing emissions from the Railbelt by 2050, as well as exploring more decarbonization opportunities on the Railbelt. And along with those opportunities, gathering more information on those resources. With those resources, also modeling them in PSSC for feasibility, which includes stability and reliability. Some of my personal goals for this project were to perform deep dives into renewable energy technologies. I chose hydroelectricity and pump storage hydro. And some of the information that we wanted to collect on these included where they're at in Alaska, how far they are from the Railbelt, as well as how much they cost to build, what their capacity is, and how are we going to model them in power system software. Cover the second one. Then another big one that I wanted to bring into this internship was gaining more experience in power systems software such as PSSE and Power Factory. I hope my project will contribute to the study as a whole, which will then work on increasing Alaska's renewable capacity, which will decrease its emissions overall and the dependence on fossil fuels, which is obviously very expensive, as previous interns have talked about in their projects. I also hope my portion of the project will create a kind of information bank for hydropower and pump storage hydro, which includes their potential sites, how much they cost, and how to model them in the Railbelt. So I went about my project by first catching up on Alaska's energy history and infrastructure. Not being from Alaska, I had no idea where anything was or even where the Railbelt was. I had a general idea, but after researching all that, where the Railbelt supplies, how many people there is, what energy resources are already on the Railbelt, I moved on to my deep dive for hydropower and pump storage hydro. For this, I wanted to find out how pump storage hydro works, as well as hydropower, find out where it's at, how much it costs, as well as how it's modeled and analyzed. And I'll get to that in the coming slides. Worked in with these, I learned a lot about PSSC and Power Factory, as well as working in QGIS to gather all the data that I got on the resources and costs. And then after that, I tried gathering everything into a one-stop source for all of my information. This is the basic. This is the basic function of hydropower and pump storage hydro. Hydroelectricity isn't that difficult. There's a upper reservoir that flows through a turbine and out, and then power is generated. This is already modeled on the Railbelt in the forms of Bradley Lake, Oklutna, and Cooper Lake. And pump storage hydro has been around for a long time, but is not anywhere in Alaska, as it's doesn't serve a huge purpose right now for a lot of the current energy resources. But it basically works as a giant water battery. When there's high load, the water from the upper reservoir flows down into the lower reservoir through a turbine, creating power similar to a regular hydroelectric plant. And then when there is low load and there's excess electricity, which creates cheap power, the cheap power is bought and pumps the excess or pumps water from the lower reservoir up into the upper reservoir. Pump storage hydro has 3 different types that I looked at this summer, including conventional, adjustable speed, and ternary. Adjustable speed is similar to similar to conventional, but you can basically adjust the speed so that it has a higher operational efficiency along a wider range of speeds. The third one, ternary, is a little more special as it has the turbine, machine, and pump all in the same shaft. It also can turbine, pump, and the third mode of operation is the hydraulic short circuit, which allows for a faster load balancing and frequency regulation due to its ability to go in the same direction. The water can move from the lower reservoir to the upper reservoir. Obviously, you can see 50 megawatts here and 50 megawatts there, but there's 100 megawatts getting supplied through the turbine. That's supplies the machine with 50 megawatts from the grid. And that 100 megawatts and 50 megawatts pumps 150 megawatts through the pump and essentially just creates a short circuit as the mode is described. Here's a representation of some of my resource maps that I created in QGIS. The image on the right shows, actually we'll start with the image on the left. The image on the left shows the entire rail belt in yellow, along with all my hydro and pump storage hydro points. The pump storage hydro points I got from a NREL report that did a resource assessment on the United States for pump storage hydro. They used GIS-based analyses with extra filters that deleted everything that was in a federal or is in federal land, such as like national forests, or if it was on a critical habitat, they got rid of that. That's in the green. And in the red, you can see the hydro sites. Hydro sites were from a data repository from the State of Alaska GeoPortal. From there, I did a distance filtering, a straight line distance from the points to the rail belt to get everything within a feasible distance. From that distance filtering, I wanted to include objects such as mountains, because obviously transmission lines aren't ideal to be sent over mountains. So I did a least cost path analysis. And in the second picture, you can see the least cost path analysis that was done with a digital elevation model. You can see how jagged these lines are, and that's just from the slopes. It's trying to accumulate the least amount of slope throughout the entire path. This is a low quality yet decent flyover of the entire rail belt. I took the digital elevation model from the least cost path analysis and laid an imagery layer over it to, along with all my data, to show where the rail belt's at. Rail belt's in blue on this one. And this one also shows the streams, which are in bright green. This can be useful for visualizing how the paths fall through the slopes as it's avoiding them. I don't exactly know where a lot of them are, but there's definitely some good examples of how it slopes through. For modeling the pump storage hydro and hydroelectric, they're very simple. Hydroelectric is similar to this bottom one. For the modeling, we wanted to do power flow and dynamic studies. And hydroelectric, since it's already modeled, we already know the machine model, the exciter model, and the governor model. The governor model is what is unique to hydroelectric and pump storage hydro, since the machine model and the exciter model are similar to existing coal plants that use a turbine already. The governor model for pump storage hydro and hydroelectric uses it regulates the speed, which is based off the speed of the water, which is from penstock dynamics. And then in pump storage hydro, additional dynamics are thrown in for conventional with the pumping mode. And in adjustable speed, the pumping mode and the generating mode can both be changed, which alters the dynamics further and creates a more complex dynamic model. And it gets even worse in ternary, because you have 3 different modes all working off of one model: the pumping, generating, and hydraulic short circuit. Some of the lessons I learned come from the challenges that I faced. One of the first ones that we came across was for version mismatches with PSSE and Python, trying to integrate Python with PSSE to increase our ability to repeat processes instead of going through the process, deleting the project, going through it again over and over again. The next one came from the ternary pump storage hydrodynamic model, as well as the adjustable. Argonne National Labs came out with a dynamic model for the governor for the ternary and adjustable speed, but after reaching out to get those models, they were not compatible with the version of PSSE that we were using. So that was kind of a dead end and a little bit of time wasted, but a lot of information garnered. Another one was learning QGIS from scratch. I had never done anything in QGIS before, so it was a lot of fun. It's a lot of fun learning it, but also a lot of issues. One of the biggest ones was with the coordinate reference system, trying to measure the straight line distances didn't work, because some distances were farther, and when they're farther, they're less accurate with the current reference system. But after 3 days of trying to figure that out, I had a half-hour call with Dane, and he fixed my problem. And now I don't have to worry about that anymore. Some of the changes that I would have made are I would have followed my plan a lot closer from the beginning, instead of going down more rabbit holes that I'll talk about in the next one. I would have also reached out a lot sooner. There's a lot of people here that know a lot about everything, a lot more than I would know. And one of the biggest examples was with Dane and the coordinate reference system. I also wanted to work in PSSE a lot more. I didn't get to, because of working in QGIS, as well as trying to find dynamic models for ternary and adjustable speed. Kind of got hooked on that, and wish I would have just worked with the conventional, as we knew how to model those. So advice for someone following my footsteps: I would want them to continuously write down their sources, as well as label their importance and what information they have in them. I did not do that as efficiently as I wanted to. It was kind of a lot of work at the end to gather everything that I had bookmarked and put it all into one kind of area. Conclusion: some of my successes, I really like that I got to create my resource maps for QGIS. Hope that they're going to be a big help with visualizing all the information about all the pump storage and hydro sites that we have selected, as well as I like learning about the hydroelectric and pump storage in depth. I never knew about pump storage before coming up here, and the information that I've gained from that, it's an insane amount of information just from learning how exactly the flow rate and the head rate works all together to create power from it. I also enjoyed gaining experience in QGIS, PSSE, and Power Factory. I don't know if I ever explained it, but Power Factory is just similar to PSSE, it's just not used in the US as much. I really enjoyed the freedom to work with, to choose the path of my own research, as well as choosing which technologies I could research into, and then create my own plan of action that would align with the deliverables and the amount of time for them. At least enjoyed falling into the research rabbit holes that included like going into one report, reading through it, thinking I found something, and then following that footnote trail just to lead to a paper that has nothing to do with anything that I'm trying to find out. Just a lot of time wasted that I could have spent somewhere else. And finally, I'm really excited for how my contribution will impact the pathways study, as well as how it'll impact the rest of Alaska. I'm also really thankful to Acep for the opportunity. Questions?
So talk to me about temperature. Like, when do we need to worry about freezing, and like when, or are these underground, or the penstocks underground, so you don't have to worry about it? I've always been curious about this.
We didn't really look at temperature for a lot of these. It was at the back of my mind, but I figured, since, are you referring for like hydroelectric or pump storage hydro? So for hydroelectric, I guess it's a lake, so the top would freeze over. And it's always gonna be moving, I guess, just a little bit. I guess we could always just look at existing ones such as Bradley for that. For pump storage, you can use underground facilities. They're not as widely used because they're difficult to make. A lot of the sites that I looked at, actually all the sites that I looked at except one, were closed loops. So it was basically looking from a GIS perspective down into where it makes a bowl, and where there's another lower bowl. So they're all going to be open air. As far as temperature goes, a lot of it's going to be pump storage hydro acts on a daily basis. So it's going to be moving up and down a lot in a single day. So I guess you will have some freezing over, but it's going to be a huge issue. It's going to be a huge issue if it gets close enough to freeze the entirety of the reservoir down to the bottom.
Did your research touch how potential changes in the climate of these regions would affect hydro and or like the rainfall in these areas?
So they did towards the end. I didn't get the data put into QGIS, but just a week or two ago, I talked to Erin about the data that I have, and she suggested adding precipitation data into the pump storage hydro database, and we were going to be adding that in later. That's true.
Just because I think it's very cool. Could you share the timeframes for ternary, like how fast it can move from pumping to generating versus the conventional, and how that relates to how it can integrate renewables faster or better?
So conventional pump storage hydro, since it is a reversible pump turbine, the turbine has to stop when it's generating and then turn around and reverse the other way, which creates for long transition times on the minute scale, usually about 5 minutes, less than 10 minutes to transition from full pump or full generating to full pumping. For ternary, would you be able to bring up the slide? I guess it's not that big of a deal. For ternary, for ternary, because the turbine is on the same shaft as the pump, if the turbine's turbining this way, the pump is rotating in the same direction but pumping the opposite way. So the ternary setup can have transition times on the scale of 30 seconds to a minute, and on the very long end of a minute and a half. It's just it responds a lot faster than conventional, and even adjustable speed is the same way. It's a little shorter than conventional, but because adjustable speed still uses a reversible pump turbine, it has a longer transition time than ternary.
All right, well, let's give Leif a huge round of applause.